Time dilation and redshift. We can't solve problems by using the same kind of thinking we used when we created them. Albert Einstein. Time dilation means slowing down time or clock. Such feature of time was discovered by Einstein theoretically and then confirmed in real life. Two reasons or cases for time dilation are very well known and compete against each other inside geolocation satellites. One discovery states time slows down near massive objects. For example, time runs faster at our head level than at our feet level, because feet are closer to Earth. Another discovery states time slows down for any moving object. Geolocation satellites require high precision in measuring time to come out with right coordinates. On their orbit, time runs faster than on Earth because satellites are farther from Earth. But because satellites move fast, time slows down there as well. Calculations show that altogether satellite clock speeds up. Because of this, satellite clocks are made to run slower intentionally, so when on the orbit, they speed up and stay in sync with the time on Earth. Redshift means regular light that is usually white, for some reason, for some observers looks red. Blue shift is similar concept when light emitted as white appears bluish to an observer. Physically that means red-shifted light wave became longer when received, and blue-shifted light wave became shorter when received. Doppler found that when light emitter and or receiver move away from each other, does not matter one or both move away, or one moves closer but another runs away faster, then the received light is red-shifted compared to the emitted. And when light emitter and receiver move in direction to each other, closing distance between them in any way, then light is blue-shifted when received. Group of astronomers led by Hubble found that majority of galaxies look reddish when observed in telescope. And the farther these galaxies from us, the redder they look to us. Their measurements were summarized in the theory stating that our universe is expanding, and its expansion accelerates. That was expressed by formula V equals hd. V, recessional velocity, h, Hubble's constant, d, proper distance. Hubble's constant is about recession rate and its value is around 70 km per second, megaparsec. Its reverse value 1/h that is about 14 billion years is better known as the approximate age of our universe. There are some issues with the theory of the accelerated expansion of universe. If it was true then the later in time, the faster space expands. And there is nothing later than here and now, so scientists measured how fast space is expanding around us, on Earth, in solar system, and in our Milky Way. And no expansion has been detected. And what are bodies, shall they expand with age too? So, the first task, explain starlight redshift, the farther star the more reddish it is, without the space expansion. And how new solution can be verified. My solution. Time was slow in the past, and it speeds up since. We'll working with z equals, wavelength received, wavelength at the source, 1. If wavelength of the light did not change then z equals 0, if red shifted then z greater than 0, if blue shifted then z less than 0. Z value is called redshift. Starlight observations look like this. We'll be talking about time now and then and about time. Time running slow or fast. Such talks might be confusing. Let me give you an example of such confusing talk at Wikipedia about tidal effects slowing down Earth spinning. 700 million years ago Earth day was 22 hours, and year was 400 days. Does it mean that day is longer now, but year is shorter now? If that is not confusing already, then let's ask what happened to a month. Has it become shorter or longer since? Problem is in the language. Let me rewrite the original statement. 700 million years ago. Their day lasted 22 hours, and their year lasted 400. Their days, meaning Earth spin faster, rotation around Sun is not discussed. Coming back to our task, how can we compare time passage now and then? For this, some kind of message is used, from the past to now. Let's say, and I'm making those numbers up for now, real numbers will come later. 10 billion years ago time was 2 times slower. Real numbers will come later. What does it mean and what is the measurement for this? It means the following. If someone who lived 10 billion years ago took 10 seconds of his time to send me a radio signal of 100 harmonics, 100 wave signal, then on my radio this signal lasts 20 seconds. In other words, clocks are ticking twice faster now, time is twice faster now. What does it mean if expressed by a frequency of the signal at the source and at the destination? At the source frequency was 100 harmonics, 10 seconds equals 10 Hz. At the destination it became 100 harmonics, 20 seconds equals 5 Hz. That means frequency dropped twice. As for wavelength, that means it doubled, because wavelength is in reverse to the frequency. By Einstein's formula, frequency multiplied by wavelength gives the speed of light constant. In the terms of redshift, that means z plus 1 equals 2 or z equals 1. Z equals, wavelength received, wavelength at the source, 1 equals 2 to 1 equals 1. This example helps to build intuition that slowness of the time in the past can be rated in 1 plus z, that is the ratio of the wavelength received to the wavelength sent. New explanation for GNZ11 observation at the map above now will be 32 billion years ago time was running 12 times slower than it runs today. And to understand or calculate that about GNZ11, there is no need to know anything about time zones in between. Hubble's and his followers' measurements can be reused for such new explanations. And since there is no expansion of the universe in my model, there is the only one distance to the stars, and not 3 types of distances as from Hubble's model. Now to the second question, how to prove my model. Let's think back. Hubble's constant 70 km per second, megaparsec for expansion rate was derived from redshift observations. Megaparsec is 3,262,000 light years. Let's recover redshift from Hubble's constant using known formula. Z equals 1 plus V slash C0 middle.5, 1 volt slash C0 middle.5, 1. Here V is recession speed and C is the speed of light 300,000 km per second. When Vc is a small value, the formula above is simplified to Z equals Vc. Hubble's ratio, x 70 km per second. X 3. 262,000 light years, for x equals 1, 3,262,000 means that recession speed in 1 year is V equals 70, 3,262,000 km per second. So, Vc equals 70, 3,262,000, 300,000 equals 7.153 times 10 superscript 1 superscript 1. Originally Hubble's measurements were about redshift observed literally. Z plus 1 equals 1 plus 7.153 times 10 superscript 1 superscript 1 a year. So, in lab experiment to confirm that time speeds up can be the following. Loop a laser light, using mirrors. Measure its wavelength at the source once. Let it run for 1 year, without any retransmission. Signal measured in a year should be the original, not retransmitted. Measure its wavelength in a year. If received light wave is 1 plus 7.153 times 10 superscript 1 superscript 1 times longer compared to what was year before, then we have in lab proof. Please be accurate with the tools used. Frequency/wavelength measurements implicitly rely on some definition of a second. That tool should not cancel out signal change that happens due to time change. For faulty tools, see Refining the Big Bang debunking experiment. I checked what is used as a second nowadays. It is defined as the time for some process in cesium-133 to oscillate 9,192,631,770 times. Interestingly enough, that the anticipated 7.153 times 10 superscript 1 superscript 1 delta in time and cesium-133 clock tick equals 9,192,631,770 have close to 10 superscript 1 0 magnitude. But Wikipedia article about this clock says that its precision is 10 superscript 16, actually accurate to a millionth fraction of a tick. That is more than enough for our experiment. With this theory of no inflation, neither dark energy is required to inflate universe, nor dark matter is required to maintain extending universe density. We got rid of dark energy completely. To get rid of dark matter completely, we are to solve one more puzzle in spiral galaxies. Similar puzzle exists for galaxies clusters, but time dilation solves them all. Let's finish this chapter with a discussion about refraction. When light wavelength changes, then light is refracted by Snell's formula. Snell's formula. If look at time zones map, line of the sight is perpendicular to TZ1, TZ11 borders. For an observer, refraction is not happening when observing remote objects, when looking into the past, because angles R and B in Snell's formula are both 0. So, we are good, no refraction interferes when observing the past. In a later chapter about black holes, we'll return to the refraction, there it plays a stealth role. And the most interesting question, why does time speed up? We leave for a later chapter, where the essence of time is revealed. Read more in free ebook Time Matters at play.google.com or at amazon.com. Refining the Big Bang debunking experiment. Even a broken clock is right twice a day. Stephen Hunt. In Time Dilation and Redshift. I suggested an experiment to prove that Hubble redshift comes from time speeding up. It is based on the fact that if a second becomes shorter, then the number of light harmonics, number of waves, decreases within a single second, and that is the reason of redshift. Clock used in the device for such experiment should be in sync with time of space for the duration of the experiment. Let me explain what that means first, and then I'll adjust the experiment to work even with a clock that is out of sync with the space-time. By now you know that second in space is defined as the time for a light to travel 299,792,458 meters. Or slash and such second is defined as time at which some process in cesium-133 clock gives 9,192,631,770 oscillations. But atomic time is autonomous from the time of space. Time speed in an atom can be different from time speed in the environment/space, and time change rate in the atom and space can differ as well. Even worse, process in the cesium-133 clock that creates such oscillations, or any underlying process in another atomic clock, or even non-atomic clock, might depend on atomic time partially only and on environment time partially as well. Process can span over atomic and space scale. Thus, there is no reason to believe that time in space and time in clock change at the same rate over the time. In the first chapter experiment, we expect time speeding up at the rate of 1.00000000007 a year, or 1.00000000002 a day, if we run an experiment within a day. That means, if clock used in the device for such experiment is in sync with spacetime always, then wavelength of light increases at the rate of 1.00000000007 a year, or 1.00000000002 a day. But what happens if clock time, atomic time, does not speed up at all? We will see no wavelength change because at the beginning of the experiment we counted waves in 1 second, but at the end of experiment we will count waves in 1.00000000007 seconds, in a longer period than 1 second of spacetime. How to resolve this issue if that is the case? Speed of light constant comes to the rescue. At the end of the experiment, if measure the distance that light travels in 1 second of atomic clock, which is 1.00000000007 seconds of spacetime, we will see that light travels 1.00000000007 299,792,458 meters in 1 second of atomic clock at the end of experiment that lasts for a year, or 1.00000000002 299,792,458 meters for the experiment lasts a day. Duration of the experiment matters from tool precision perspective only. Tools used in 1-day experiment should be 100 times more sensitive than tools used in 1-year experiment. Now we have two variables, rate at which time speeds up in space over the duration of the experiment, let's denote it d space, and rate at which time speeds up in clock used in the experiment, let's denote it d clock. We should double check the clock setup at the beginning of the experiment, by checking what distance does light travel in 1 second of clock time. Let's assume that a cesium-133 clock is used, and at the beginning of the experiment, I would double check this value anyway. Light travels 299,792,458 meters, or whatever TD_start m, in 9,192,631,770 clock oscillations. Let's say, light emitted in the experiment had WL_start wavelength at the beginning. Then at the end of the experiment we measure distance that light travels in 9,192,631,770 of clock oscillations, TD_end m, and we measure light wavelength WL_end as well. 4 values should be noted as the result of the experiment. TD underscore start, TD underscore end, WL underscore start, WL underscore end. These values are related through d space, rate at which spacetime speeded up in the experiment. If it stayed the same then d space equals 1, if it slowed down then d space less than 1, if it speeded up then d space greater than 1, and d clock, rate at which clock time speeded up. If it stayed the same then d clock equals 1, if it slowed down then d clock less than 1, if it speeded up then d clock greater than 1. WL underscore end equals WL underscore start d clock dot TD underscore end equals TD underscore start d space, d clock. Multiplying these two lines we get WL underscore end TD underscore end equals WL underscore start TD underscore start d space dot. And d space equals WL underscore end slash WL underscore start, TD underscore end slash TD underscore start. Type of the clock used does not matter. The same clock type should be used for wavelength measurement and speed of light measurement at the beginning and the end of the experiment. Duration of the experiment, day or year, should not matter, if instruments are precise enough to catch the difference between the beginning and at the end of the experiment. In the first chapter we assume that TD underscore end slash TD underscore start equals 1. Which means speed of light does not change, for the clock used, meaning clock time is in sync with spacetime during the experiment. No such assumption on clocks anymore. Read more in free ebook Time Matters at play.google.com or at amazon.com.